DTP, corner, and say. So what I'm going to talk about is the kind of a program which I've been following with many of my collaborators. The idea is that if I go beyond general relativity, if I add higher curvature terms to the Einstein universal union, whether there is a suitably defined generalization of the Hawking's quote-unquote area theorem, because of course, as we all know, entropy will no longer be the proportional area. So the question is, assuming that other technicalities hold, can you prove an analogous area theorem with the entropy functions? Of course, a priori, this question has nothing to do with holography or anything. It's a question related with the black holes. You can ask this question in asymptotically flat spacetime where you may not have any holographic analog of anything. And it's an important question in the context of the general relativity for black hole mechanics, classical black hole mechanics.
Just to understand, sorry, I'm sure you'll explain this, but when you say higher curvature gravity, you're including those terms in the action, but not including loops. Is that right?
What do you mean by loop? These are perfectly classical. Just like higher curvature R squared. So in string language, there will be no GS on the R squared. And it turns out that, but in case what we have found that if we put these black holes in ADS, and if we ask second law for these black holes, or ADS, asymptotically ADS, then there is a very interesting relationship with holographic, particularly the holographic entanglement entropy arises, which was a bit surprising for us because we are not much, the people, the group I have worked with is not a string theory group, so we had to actually talk to string theory, for example, to learn this stuff. So let me start with this. So this is the plan of the talk. Of course, I start with the usual interaction for any black hole thermodynamics talks. That Wittgenstein's idea, then I talk about black hole mechanics very briefly. I talk about higher temperature correction terms, and I talk about the linearized second term. So when I say ambiguities, I try to explain that what do I mean by ambiguities in the construction of the word entropy. Then I'll say what do I mean by the relationship with holographic entanglement entropy, which a priori has nothing to do with black holes also. Then I'll go beyond linear order of perturbations for black hole, and there should be a R here. Okay. Then I'll talk about constraints, which one of them, if I want second law to hold true, then it turns out that it cannot hold true in general for any value of the higher temperature coupling coefficient. There is a range which has to be satisfied. It turns out those constraints, in some cases, exactly matches with the constraints obtained in the ADS-CFT, I mean, in the consistency of the boundary theory in terms of causality constraint or unitary constraints.
Again, I should wait, but just to ask you, I mean, if you view the higher curvature terms as kind of part of an effective action, then what is the significance of a result beyond linearized order? That is to say, to the extent the higher order terms are more than a small correction, you should really, if you believe that there is a more complete theory which includes arbitrary higher order terms.
This linear order doesn't mean linear order in the action. It's in the linear order of the perturbations of the black hole.
Yeah, that's what I thought you meant. No, that's what I thought you meant.
Yeah.
But if you're going to be, let's say you had an effect which depended on the R squared term at linear order in the perturbation, and now you're interested in consequences at a quadratic order in the perturbation.
Yes.
Wouldn't they involve the R squared term beyond the leading contribution?
You mean it may involve the R cube term?
Yeah.
Of course
there would be.
Of course, right? I think you are right.
So if you at least were, let's say, a string theorist and you thought of the effective action as just, it's higher and higher terms, what would be the significance?
I'll come back to the issue. So what you are saying is that actually if you really want to understand this constraint, you should add all orders.
Yeah.
And I'll come back to this issue. In fact, this is something to do. So it could happen that this higher temperature theory, truncated at a finite order, all of you know better than me, it may not make sense because there will be serious consequences regarding causality. This one is in a command note paper. So I agree with you.
So Anosh, I agree. Are there two separate expansions, the derivative expansion, like the alpha prime expansion? For instance, in n equals 4 angles, one can work at any given value of lambda, and then at that value of lambda, the field theory is completely well defined, and work to all orders. And
no, I think what Sandeep, as I interpret as Sandeep is that if I add stuff, for example, stop at any value of the alpha prime and calculate this constraints, it could happen that constraints may change if I add another higher order in alpha prime. I think that is what I meant.
So you have to work order by order in
order by order
expansion. But at any given order, you can work to what order is lambda.
Yeah, so there are two different perturbations, but
sure, but if you're going to derive constraints on the higher order corrections that you want to be independent of possible things you have left out, then I'm just saying if you look beyond linearized order, that's in amplitude, I doubt that you'll be able to.
In fact, not only that, it may even happen in the linear order itself.
Okay, it could happen.
Even it happen in the linear order.
Could happen, but certainly
because the entropy will change once you add R cube term.
Could, but certainly in the non-linear order, I think.
I presume that it may happen, but there are two different perturbations. Maybe
okay, but let me make it. Sorry, you should go on. Let me say why, because this is in the context of a discussion. We should have this is happen. The time when the linearized constraints are sensitive to the higher order corrections will be, I think, but you will correct me, I'm very sorry, for adiabatic processes. Where the leading term, is giving a contribution which is sort of on the edge.
Okay.
Because the leading term itself gives a contribution, then you can't get a constraint on the corrections. See, because they're small. How do you get a constraint?
I understand, but what happens is
just to complete. Therefore, if you're looking at such adiabatic processes and you go to linear order and you get a constraint on the higher derivative, and now you want to get a constraint from non-linear processes, that will be say second order in the higher, for which a R cube term might be also involved.
That's where I was true. I think that is probably true. So what? I think that is probably. Maybe I'll go into the calculation.
This is one comment. Exactly the same issue arises when trying to constrain the entropy current in hydrodynamics. Hydrodynamics is a derivative expansion, and at any given order in the derivative expansion, you can ask about constraining. So then it's up to now. This is great. And what you're saying is, of course, partly right, but not 100%. I mean, there are.
In the parameter space, if you introduce another parameter in R cube,
it's because there's an infinite amount of data in the flow about a given point. Because you want not just you want something to be adiabatic at that point. So all is there. Anyway,
sorry, I apologize.
But I'll come back to this when I actually explain to you what it is. So let's start with the first slide. So obviously there is no point of this first slide in this audience, but let me just. So general relativity says gravity in curved spacetime, and thermostatical metric which represents the gravitational field of the spacetime. The idea is that the general relativity predicts the light cone structure will be affected. The causal structure will be affected in the presence of matter, and we all know that the R equal to 2 is a causal boundary, and outside observer has no access, classically at least, for the inside information, what is happening inside. And technically, you would define in asymptotically flat spacetime, when the asymptotic structure is known, you will define the event horizon, the boundary of the black hole region as the complement of the past null sky plus, the future null infinity, and then technically the closure of this boundary and its closure will be the event horizon, and then there is out region and out in region which are causally disconnected from each other. Note that the event horizon is a global notion, in a sense that you have to know the history of entire sky plus to construct the event horizon. It's peculiar. I don't think it is pathological, but it's just peculiar. There is no local experiment by which you can say whether you are already in the event horizon or not. But in the context of second law, it will be important. It means you have to put certain global boundary condition to get the result that area is increasing. Those boundary conditions may mostly the general relativists would love to write it in the form of the cosmic assertion. And I'll explain why boundary conditions that way. So once you define event horizon according to the complement of the past, future, and infinity, there are standard result in general relativity which says it has to be a null hypersurface generated by null geodesics, and these are future complete generators. In the sense that there is no caustic in the future. It says that if you add, you can add always matter to the, you can add always new generators to the event horizon, but you cannot remove generators because you know that if you can do it, you will probably violate the calculation. So this result proven long in 60s and 70s, like those classic references, of course, talking about. So you want to install a coordinate system on a null surface. This will be required for our mathematical structure when you prove the second law that we introduce the coordinate system, which I will do. So the null surface is a codimension 1 surface. It's a degenerate surface. So you go to the codimension 2 cross section of the null surface. You introduce 2 null vectors. So K is along the generators. So this generates the null surface. And LA is another null vector. That choice is arbitrary because we could have chosen LA anywhere. Okay. there is a freedom involved. So this K and LA is a null basis of the plane perpendicular to the d minus 2 dimensional codimensional cross section of the event horizon. And this is the induced metric, the pullback of the spacetime metric on the event horizon cross section. Remember, this is d minus 2 dimensional metric, Euclidean metric. And then the spacetime metric in this coordinate system, you can write into this 2 into d minus 2 decomposition. This is analogous to 3 plus 1 decomposition, just since it's for null surface, it's 2 plus 2. That's all. Then you define what is called the expansion of the null surface. This expansion along the direction of Ka, which is change in infinitesimal area per unit infinitesimal area. And then there is a Ricciardi equation which determines the rate of change of this expansion as a function of the geometry. It's completely mathematics. There is no way physics goes. So physics will enter here. When you liquid, use Einstein's equation. Before that, it's a standard statement of geometry. Note that if you have a stationary null surface, the so-called non-expanding null surface, your expansion will be 0. So basically, you then end up identity 0 equal to 0. So this is the mathematical structure. Of course, the shear is the shear associated with this null surface, like cross section. So as you can introduce expansion along K direction, you can pick up another convergence and expansion of LA direction is also possible. But that LA may not be 0, even for short-term spacetime. That LA, for example, if you throw light rays into the black hole, that has an expansion. So that expansion will be negative. And if you calculate it, it's a minus 2 by r. So that is, the area is decreasing. So here is a null surface whose area is decreasing. So it proves that not all null surfaces area increases. Okay. So all null surfaces don't have entropy. You just can't ascribe entropy to null surfaces. The event horizon is special because there are boundary conditions which will put in the future of the event horizon. So of course the history, all of you know this great idea of Bekenstein, what will happen if I throw a highly entropic object into the black hole? How do I save second law for the outside universe? And of course the idea is that you ascribe an entropy to the black hole horizon. Black hole block information, they must have an entropy from entropic information point of view. And then there is this very naive argument, but this argument makes no sense if you think of it. But I just want to show you because it gives you one line motivation why black hole entropy will not be proportional to area when you go beyond Einstein. That argument is very simple. Suppose it's a naive argument. Let me be absolutely clear. But consider a black hole formed by the collapse of a star of mass n. Now suppose this star consists of atoms of mass small m, and each atom consists of 1 bit of information, like it's a spin state or something, some internal degree of freedom. So you collapse it, the outside observer loses that information. How much information you have lost? You will lose capital N by small m. How many atoms you have? 5 atoms, 1 bit. So you will say, okay, this much loss of information, this is my rho and rho. So in some sense, this is my entropy. I'll ascribe to the black hole. But of course, classically n could be as small as possible, but if you use this naive quantum mechanics, you want that the Compton wavelength of the atom should be less than the horizon radius. So there is a limit. This is like very old argument. Okay, we don't do
it would be much less, right? You could throw an electron into a solar mass black hole. So the mass little m could be
very large, but then you don't
much smaller.
But the point is that
you want a bound.
You want a bound. You want that the small mass should be such that the Compton wavelength is less, so that you say that it is confined within the black hole.
Okay.
So in that case, if you put the bound, then you can show that the entropy is bounded by this value m RH by H1. It's one line. So it says that nowhere I have used any general relativity other than saying that. Now, if you don't use any field equation, the field equation comes when you use Schwarzschild solution, when you say RH goes up. Again, this is very nice. The point will come in one line later. RH goes as m, and then entropy goes as RH squared. So this you can think of without the field equation. If you are a particle physicist, you will say that option result. Okay. And this is kind of unsure. So black hole entropy in general relativity is proportional to n. Of course, this is a good news because if black hole entropy is proportional to area, then there are this classical area theorem in general relativity by Hawking et al. I think Hawking. Okay. That area theorem ensures that certain technical conditions satisfied, the area will never decrease. And what are the conditions satisfied? Of course, non-energy condition on matter field that is required, the classical energy condition, and some form of cosmic succession. This sum is very, very vague. Even in GR literature, cosmic succession is, it's vaguely defined. So let's see what will serve for our purpose. So if Rayachandra equation, it just says it's a second derivative of the area. It says d theta d lambda is negative. It doesn't say anything about the first derivative of area. So if you want to integrate this equation, you require a boundary condition. And there comes the importance of the event horizon. That is why this is true for all non-surfaces in the universe. Theta decreases, but it is definitely true. The second step, when you integrate the equation and put a boundary condition and impose a condition on theta, that is true for specific non-surface, and event horizon is one of them. So cosmic censorship or non-completeness prohibits what is called the caustic in the future event horizon. You say that the course of the evolution, there is no caustic in the future. So theta cannot diverge to negative infinity. Otherwise there is a caustic. Let's think of that. So now will not intersect. If you do it, there are this thought experiment you can show. You can see the singularity from outside. If there will be 2 points in the event horizon which will be time-like separated. Once there is a caustic. And then you can bring the light from outside, inside to outside, and of course your physics is in danger because your Cauchy-Theta evolution will hit wrong. So if you impose that condition, of course, then you can show that theta cannot be negative infinity in the future. That's a boundary condition, and therefore theta must be positive. So the only possibility exists that theta is positive, so area is increasing, but the rate of change of area is decreasing. So area increases and ultimately reaches to a zero, constant value.
Because theta, d theta or d lambda is less than negative. But theta cannot get to minus
infinity.
So
suppose you start with somewhere theta is negative. So theta will decrease. And it will decrease and suddenly hit negative infinity. That is not allowed by compressibility. So theta cannot be negative anywhere in the future, past. It's a time evolution of theta. Theta is always decreasing.
Suppose it were slightly negative, why can't it then decrease?
Because it will always decrease, because this is true.
Yes, I agree, but why does it have to be positive if it can't be minus?
Because if it is little bit negative,
it doesn't reach minus infinity in the far past, in the far future.
No, the point is that Rayachandra equation says it will reach any slightly negative value. It will reach.
Okay, just to understand, what happens if it's positive? It can't become negative?
It can't become negative. Because once it reaches zero, then it's a stationary black hole. You end up having 0 to 0. 0 equal to 0. So you put a boundary condition.
I'm sorry to be so close.
Sorry. So
the right-hand side of that equation
is negative. Because you impose null energy condition to make it negative.
I suppose it started slightly positive.
Slightly positive. Okay. So then the idea is that it will decrease.
Okay, and suppose it hits 0.
So then you have to put a boundary condition that if it is 0, then theta is 0, sigma is 0, and the perturbation, it's a boundary you have to put by hand. Otherwise it will not happen.
That's what I was asking.
You have to put by hand.
That term, I don't know that much about the shear right away. That term certainly is determined by the matter.
So you impose a condition there. This is your perturbation. You impose null energy condition that it is negative. And if it is positive, you impose a boundary condition that it will go to 0 in the at infinity, when lambda goes to infinity. This is motivated by the cosmic censorship, and for linearized case, this is just stability.
This is a very sophisticated way of saying, it's a very GR sophisticated way of saying it. But let me just say the way I would say it. You know, black holes settle down into equilibrium. So at late times, theta is 0. Since d theta by d theta is negative.
Although, I will just object to one statement. That is true as long as you are considering linearized perturbation.
Why?
Because there is no proof that generic black hole will settle down to, unless, for example,
I'm just interested in what happens.
Okay, so let me take a statement. For example, if you believe in positive mass theorem, and if you believe in Kozinov mode's correct sign of Kozinov mode, you know that linear stability. But there is no such proof beyond general relativity, and so therefore I will use this language.
I know, it's great language. Just convey it. You know.
Now, I was wondering how it is working for theta slightly positive, but I understand in that case, you just make it go to 0 as well.
So the point is that the area theorem ensures that when you throw an entropic object, the total sum, what you throw, the entropy of what you throw, and the area of the black hole, that total sum cannot decrease. This is what we general relativists would call generalized second law, but you will think simply just second law in a system, in a room with a black hole. Just second law. But just historically it is called generalized second law, because Hawking area theorem was called second law. So generalized second law is a quantum statement. at least semi-classical statement, because it involves the entropy of the outside world. Okay, it's not just A by 4. And going from second law to generalized second law is, it requires at least a prescription. How do you calculate the entropy of the outside field? Some one-to-one entropy prescription has to be given. There will be singularities at the horizon, so you have to say how those singularities will be tackled. Actually, I can tell you what happens very naively, that if you calculate the difference, the singularity part actually goes out. This is there in the world paper and that's one paper, that you can show that there is a way to define the generalized entropy, but I'm not going into that. The whole point.
Why can't you at zeroth order just be the thermodynamic entropy outside coupled with the Wittgenstein-Hawking entropy?
Coupled means adding. Yes, but
because if you're going to make it quantum, I know it's often stated like a semi-classical, but then the right-hand side of Raychaudhury's equation, it doesn't satisfy the null energy condition. Yes. Black hole area shrinks, and we know you hit a singularity where nobody knows really what happens. But this curvature goes to Planck scale, so nobody knows what happens.
But the way
none of those conditions you state.
But the way that it said that since black hole actually radiates radiation, and therefore in some Urdu state has negative energy, quote unquote, the expectation value of energy momentum tensor is negative. So therefore, if you take into the entropy of the radiation, then you have to make a statement like this. Otherwise, you are not taking into the Hawking effect.
At zeroth order, if you just set thermodynamic entropy.
But the problem is then how do you ascribe temperature then to the black hole? If you say thermodynamic entropy, you have to ascribe temperature.
I was just trying to say, if you wanted to start with a zeroth order statement which didn't necessarily involve quantum mechanics, couldn't you try to do that?
That statement is area theorem, which is a classical
area
statement.
Plus stuff outside.
But okay, but it could happen that outside stuff violates energy conditions. Say, for example, quantum field. Suppose you are doing. Okay, you are saying the classical stuff.
Yeah, good energy condition, classical.
I'll tell you there is a problem.
Okay, but you should go on.
I'll just maybe I can't stop myself in saying this. Yeah. So there is a very interesting paper by Anu and Ward. So you actually take a classical radiation gas. Now you say that you must have a condition that the entropy which you are throwing in, if it is classical, must be less than the area which is increasing. Otherwise, the total, you are again having a problem, right? So Wittgenstein, in his old paper, you see,
must be less.
I mean, total change must be positive.
Must be positive. If the area increases by more, all the better.
So you have to have always area increase more than the entropy.
Yes.
Now, what about very high entropic objects? So Wittgenstein come up with a thought experiment saying that you can create such objects which are very high entropy, which will be not compensated by the area. And then he postulated what is called this Wittgenstein bound. That you can basically, there is a maximum entropy in the universe, which is coming from your classical sector. There are explicit examples of even ordinary thermodynamic gas physics, which you can think of a system which is not pathological but violates Wittgenstein bound. So if you stick to this classical statement, you will have problem. More than that, what Ward and Nunu shows that you don't even need a Wittgenstein bound. If you consider, for example, the effect of the radiation, the black hole radiation.
Oh, sure, of course, because then, of course, the mass increases.
So
no, that's for sure, of course.
So this classical statement will work, but then you have to impose certain form of Wittgenstein bound. That's what I'm saying.
But if you want to make it quantum, then you have to define the entanglement outside.
Exactly.
And that's a cutoff dependent.
That's a cutoff dependent.
How are you going to compute it?
That is definitely true. So semi-classically, if you only consider...
But even semi-classically, the entanglement diverges.
Yes, of course it diverges, but for free field theory, when you do not consider interactions...
Even there it diverges.
Of course it diverges, but you can show entropy change is well defined. Entropy may not be. The change...
I mean, I don't know, if you are adding the entanglement outside to the area, the entanglement is a divergence.
Yeah, so you put a cutoff. You put a hard cutoff. So everything is dependent on cutoff.
But then you don't have a well-defined entropy to begin.
I don't say well-defined, it's a cutoff dependent entropy. There could be a cutoff, we don't know. But it's a cutoff dependent entropy. But the problem...
How do you know that there is any kind of law if the entropy in the first place we are starting with is not cutoff independent?
So see, the entropy...
I'm sorry, this
is a hard issue, that entanglement entropy, even ordinary entanglement entropy is diverges. So it is definitely true unless you put a by hand a cutoff. For example, you don't even have a well-defined area law. In condensed matter physics, maybe you can have a cutoff, real cutoff. But in black hole case, okay, honestly, you close your eyes and
I mean, the only way it makes sense is what people try to do, that if you then change the cutoff, the entanglement part will change, but the Newton's constant will also get renormalized.
Yes, so this is
such that
total entropy is cutoff independent.
But I don't think it has been made to...
No, it is never shown precisely. It is never. So for example, this is also related to the species problem. You fix your cutoff gave 1 by a by 4 and then you add another field. What will happen to that? Hope is that there are one Suskin's paper, I think, and Jacobson's paper where they show it in certain special cases. Because simply the calculation also is very difficult. How do you calculate for general field theory? That issue exists, definitely.
Sorry.
No, this is absolutely. So as I said that, so as you can see this, in classical general relativity, you can define this law. This is the first law for black hole. Okay. It does not fix the temperature because you can always add 36 here, divide by 36 here, you will get the same thing. The semi-classical calculation indeed fixes the temperature to be the Hawking temperature, and you don't know the Hawking resistant entropy, unit of the Planck length, 1/4 of the area. That's standard story. So let's go beyond general relativity. So at this stage, I am thinking this as just a classical action. So it may not have anything to do with alpha prime corrections incidentally. We all know that of course there is a quantum rationale. You can always add this term. Nothing prohibits you from adding this term. Just looking at a classical thing. You may say that Einstein and Hilbert choose the simplest thing. I want to do the hard thing. But there is a rationale. This effective field theory, non-renewable theory. So you want certain scale higher dimension operator will come into play, quote unquote. But note that once you add this higher curvature terms, there are dimensionful constants in the theory, new constants, which are the appropriate dimensions of length. Remember that result which I told you that M and RH, this is kind of optional entropy. Once you put field equation, RH goes as M, you get S goes as RH square. Here, if you do the same thing, there are more possibilities because you have new dimensionful constant. For example, this is a perfect possibility between mass and radius. And in that will make the entropy goes as area plus something which is subleading in area. So the fact that there are new dimensionful constant will allow more terms in that. Of course, you cannot, this is just naive dimensional argument. But the point is that there is a possibility that black hole entropy may not be proportional again. Of course, we don't do this way. We do the way Wald has told us to do. So what is this called? The equilibrium state version of the first law, where you actually look at, given a stationary black hole, in the phase space, you do a Hamiltonian formulation of general relativity and ask this question that, given a stationary black hole with what is called a regular bifurcation surface, that certain regularity condition on the bifurcation surface, if I look at its variation in phase space, remember this variation is in phase space, so everywhere it is stationary when you do the variation. Okay. You evaluate the variation on the stationary black hole. Okay, this is important. And then you can show that there is a first law you can define for asymptotically flat case. So note that this is highly non-local. So this side is defined at the infinity. If it is asymptotically flat case, it is defined at I naught, the space-like infinity. So this is variation of the ADM mass. This is the variation of the ADM angular momentum. You can think of. Okay, and this is evaluated at the bifurcation surface of the black hole cross section. Okay, so this is highly non-linear and classically non-linear. And then there is a prescription that I give you a Lagrangian. This Lagrangian is a function of metric and curvatures and so on and so forth. You take a partial derivative with respect to curvature, fixing the metric, so you treat metric and curvature independent, and then put it into this equation. So these are binormal, these are area 2 form, skew symmetric area 2 form on this cross section of the horizon. And then you calculate this quantity, appropriately normalize it, so that you get a by 4 for general relativity, and this is what is known as the Wald entropy. And this Wald entropy is related to the Noether charge of the Killing isometry. Because there is a Killing symmetry in the stationary spacetime that defines a Noether charge, and basically it is the integral of the Noether charge. It is guaranteed that it will be a local quantity. In a sense, it will only have curvatures and local values of this, and it will obey the first law in a stationary set function. And you can see that in generally there is no reason this to be, if it is an R square, it will contain curvature correction, no longer proportional. proportional to area beyond. So this argument clearly shows, at least for asymptotic flat case, and there is a suitable extension in ADS case where the asymptotics are well defined. You can prove very generically under certain technical conditions that the entropy of the black hole from first law is not proportional to the area.
Sorry, just I should know this, but in ADS the same formula won't apply if you have a stationary black hole.
Yes, but you have to have ADM, suitable generalization of the ADM mass.
For the mass, but the entropy is
exactly same formula applies. So you have to prove it that in suitable generalization the same formula applies, and it is classical, so there is absolutely no problem. I do not still know that there is this Azteca version of ADM mass in DS, but I haven't across that whether this. See, it's actually very easy. So basically, you look at the right term, the Hamiltonian, you prove that the bulk of value of the Hamiltonian is zero because of different repermutation in this void derivation. So then the point is that there is a boundary value at infinity and there is a boundary value at horizon. They are same. Okay. Now, boundary value for the horizon, when you put this stationary, regularity, all those things become kappa into delta S. Boundary value at infinity, when you put asymptotic flatness condition, becomes equal to 80 Hamiltonian. You have to show it for DS boundary condition that it becomes that appropriately defined, which generate the time translation at infinity. So DS time translation at infinity. So, well, so now field equation has changed because the theory has changed. There is no more area theorem, which is good because otherwise you know the entropy has changed. So you want how to formulate a GSS or say second law, classical second law, which is higher. And you need it because at least we have exact black hole solutions in this higher curvature terms. So you can formulate the 70s paradox by Mr. Wittgenstein, and if we want second law to hold true, even in a naive sense, we want to know whether there is a suitable generation of the Hawking area theorem. You can ask more interesting question. For example, whether with this term, say, does this theory make sense? Even classically, forget about quantum mechanics, does it have a positive mass theorem? For example, if I add 5-dimensional Gauss term, for R squared term, there is a paper by Horowitz shows that. See, the f of r, any R squared term is much easier because there is a field definition exists by which you can write it as a general relativity as scalar tensor theory, basically. So then many of the proofs, translate into one each other. But if you have a generic higher curvature term, what are the constraints on when you say positive mass condition? This because this is stable in this case. So,
sorry, again, you should be better informed. If for any f of r, that is true that you can use the definition?
No, there is a condition that f prime r must be positive. Which is that condition, because when you invert it, all this comes in the denominator. So that condition has to be true.
So, okay, maybe it's not very related. In the CFT, what is the dual of this higher curvature black holes?
Honestly speaking, I don't know, but I'll give you some vague answer. So, for specific theories, like for example type 2B theory, you can have a specific higher curvature terms coming from string theory.
Yeah.
But in generic case, I don't know whether all higher curvature terms in principle, Shiraj can comment on this, can be embedded in the string theory calculation. For very specific higher curvature terms, alpha cube are to be Wild tensor to the power 4 terms come in specific context. But is it possible that all higher curvature terms can be embedded?
Sounds very unlikely.
Unlikely, because there are constraints on higher curvature terms, make it difficult to. So that's why I'm saying that don't think of it that is all the semi-classical limit or the classical limit of the string theory. Treat of them as that theory of their own. Okay, where was I? So you can ask these questions that how far is there a constraint?
Just to say that's one of the reasons to be so interested in this question, because it's possible that you could unravel a structure of consistent relations in the alpha prime expansion corrections to executions just from low energy constraints.
If that happens, that is right.
We can test.
So I'll come back to what is called as here your questions will come, the linearized second law. So there I will definitely say that black hole I believe in linearized perturbation step. So this is the direction of time. Think of lambda as kind of a fine parameter on the null surface, which is like a time on the null surface. So this is where lambda equal to 0. So I start falling matter falls into the black hole. Okay. So you know that the global properties of the event horizon make it mandatory that the event horizon starts seeing this infalling matter before even the matter enters into it. So it's just definition. So this is the unperturbed event horizon. If there was no infalling matter, event horizon would have been same, and think of this length to be some kind of area. So area don't change. Since there is a infalling matter, the event horizon will start responding and expand, and you impose a boundary condition at some lambda equal to lambda f, final state is again stationary. So it's kind, you take a fluid, you tinker it, you believe the dissipation will take care of all the modes will die down, and you end up with a stationary feature. But
could be asymptotic.
Could be asymptotic, but it could be a glass, but
no, I just mean things will die out exponentially.
In fact, that kind of thing happened for black holes. Decay is exponential of number of roots. Unless you put ADS kind of boundary condition, so it's a function of boundary conditions. So
but even there
things happen, but you can presumably think of a very complicated one because the quasi-normal modes are a function of the future boundary. I think asymptotic boundary conditions also, not only on the black hole. So you can think of presumably a crazy boundary condition where it is power law. For example, the Price's law will change in different settings. I mean, the fall off of the gravitational productions. So linearized second law, you ignore theta square and sigma square because theta and sigma are linear ordered perturbations. Because there is a perturbation, there is a theta. So you ignore them. So you have only d theta dt is minus RTD Ka Kb. Ignore the 4 pi or 8 pi, you have minus Kb Kb. Again, it is negative. It's quite another condition. And then the original argument goes through since in the final state you want theta to be 0, you must have theta to be positive. Right? Which implies every slice prior to the future that theta is increasing. Now look, this is actually, I get very confused here because in ordinary thermodynamics, you don't want that entropy to increase at every instant of time. It is sufficiently okay that there is a probability that entropy could decrease. But the total entropy change must be positive. This is something more. It's actually saying, strictly saying, if null energy condition holds, every slice the theta is positive, every instant of time.
You know, in hydrodynamics, the same. Hydrodynamics, there's a positive divergence entropy curve.
And I'll come back.
Every point in space and time, entropy is always produced.
I mean, the divergence is positive.
And probably for the same reason, that classical hydrodynamics is justified by having Avogadro number going to infinity.
It is probably, the black hole is probably a dual map of them.
Yeah.
Okay. But this is one, it's an important point. It has to be taken care of. Now there are some technical points. The derivation of black and world entropy requires stationary killing horizon with regular bifacial surface. For example, if your theory have a, say, vector field, say Einstein ether theory, when there is an extra vector field, it's a diffeomorphism in very theory, but there is a vector field. Those theories, it is very difficult to define world formulation because any vector field, if you want its boundary at 0, that vector field will have infinite Lorentz boost near the bifurcation surface. Because bifurcation surface is like an infinite, any time-like surface, you can think of going infinite boost at the bifurcation surface. So if you have an extra vector field, it will not be well defined at the bifurcation surface. So the regular bifurcation surface condition will not work. So it's a strong condition. It is not trivially satisfied. That's what I'm saying.
With the condition, you need a stationary killing
factor. So maybe so here is a stationary killing horizon. Here is a bifurcation surface where your vector field is 0. Okay. You want all your matters in your theory to be finite on the black hole. So for example, if you have a time-like field, the extra field, not the part of the space time, it has infinite boost here. So
what was it? Avogadro number going to infinity in the picture that locally everywhere increases?
It's because there are no flux. You know, the entropy of course fluctuates. The fluctuations are suppressed by 1 over So entropy tries to constantly increase, but there are fluctuations. Those fluctuations are suppressed by 1 over square root of Avogadro's number. The limit Avogadro's number goes to infinity. They're described by an effect of classical theory. Classical theory could be like Boltzmann equation on long wave that limit hydrodynamics. But that is the property that because you're ignoring the fluctuations, entropy is steady. So the same thing, it's like the algorithmic classical.
So in a sense, the entropy is defined by current. Then you call a hydrodynamic limit has been achieved. So now the question is that, if you look at world entropy construction, there are several ambiguities. What are the ambiguities? So maybe I can write one of them. So for example, if you take this Lagrangian, think of Lagrangian as a D form in D dimension. You can add Lagrangian to exact form. Okay. That's one ambiguity. You can show this ambiguity does not matter as long as you have stationary black hole with regular black hole. So all these conditions are used show that whatever you add, this formula will continue to give the same result. You may think of, for example, I can add with this formula. So this is another. You can think of this as a 2 form or n-2 form because this antisymmetric tensor going up. You may think that I can add in this 2 form. So you can write down that equation to be like this, where QAB is del L del IBCD. Okay, I should say CD. Okay, doesn't matter. Okay. You can add with this Q another exact form. As long as your black hole surface, this B, this cross section is compact, it doesn't matter.
But don't we also make some assumption that mu also vanishes? It satisfies the stationary killing property.
So what is happening is that all those forms turns out to be a function of same. So there is matrix and some Lie derivative of the matrix. These are constructed out of them.
Okay. Then it works because the metric has these properties.
Yeah. Not only that, there are other ambiguities. For example, if you look at the world's derivation, for example, world uses that your the variation of the Lagrangian will give you E into G plus some d theta. But this is I-1 form, which is the surface term, the Hawking-Givers term in some sense, and this is your equation of motion. This G being the matrix. You can think of any field. What happens? You can add with this another form. Right. So there are several ambiguities. None of them matter as long as you are evaluating it with honest to God stationary surface black hole with regular perfection surface. For example, why regular perfection surface is important? Because you not only want to evaluate entropy at the bifurcation surface, you want to evaluate at any arbitrary cross section. What guarantees you that you are going to get same station? So you want that stationary black hole should have same area or same entropy at every cross section because the cross sections are related by killing isometry. These are the orbits of the killing curve. What guarantees that this will be true? Provided if you have everything is regular on the bifurcation surface, you can construct a Lie derivative, Lie map, which will take regular things to regular things, and then killing isometry ensure that if there is a bifurcation surface, the rest, the difference will dissipate.
And can't you just, you can't wiggle yourself?
You can wiggle yourself. You can wiggle yourself. It has to be compact, but it need not be. It could have, the.
You don't just translate the first surface out. You can.
So in the sense that it
how
could be.
How you cut doesn't matter.
It's a what is called a non-extremal cut.
You don't cut along slices of constant.
No, you don't need constant extrinsic curvature on those slices. Those extrinsic curvature on that slice can also vary. It doesn't matter. So this is what we call the non-extremal slicing.
See, in case of the Hawking area form, this is here because there's there's the area form and then there's null direction which carries no area.
Think of this. So this is infinitesimal.
The middle in that direction doesn't matter because it carries no area.
Okay. Now, all those ambiguities I can package, okay, and need to write down into this. So let me define. So this is my notation. So this will be important. I give you a Lagrangian. You calculate this quantity. I will call it Wald formula. Wald entropy. This is just a name, okay. Once I give you a Lagrangian, you give me a Lagrangian of your theory. Use this formula, whatever result you get. Okay, I call it a Wald entropy. So this is important because I will use different other entropy. Now, the black hole entropy, I will write Wald entropy plus ambiguities. Now, this ambiguity structure is important. Note that. This ambiguities involves product of theta k and theta l and sigma k and sigma l. Note, if you are in stationary black hole, theta k are 0, sigma k is also 0. You are stationary black hole, and this is the generator of the event horizon. And then this is exactly Wald entropy is equal to black hole entropy. Why only theta k, theta l kind of combination? So you can think of rescaling k and l as a Lorentz transformation. So if you rescale k by lambda and La by 1 by lambda, that is like doing a boost.
This is what is the right hand side now?
So this is void entropy. I define black hole entropy as void entropy plus all possible ambiguities packaged into this coefficient A and B.
Still for stationary solutions?
This is not, this is for general, so these are ambiguities.
Okay.
These terms will vanish if there is a stationary black hole. So then void entropy is same as the black hole entropy. But in non-stationary case, you can have these terms.
Is this meant to be a local formula or a global? I mean, is this meant to be along the slice or at a point?
So I have written it a bit wrongly. I should have called it entropy density. So it is integrated over the slice.
So this is a local one.
This is a local quantity. So I should not say S here. I think I should say that small s or rho. So maybe I'll write it a little bit carefully here. So your yes, thank you. So I will write entropy to be integration over the codimension 2 surface of an entropy density over the area form. This entropy density I can write as void rho w plus this terms. So this is indeed local in a sense. Okay, I should say quasi-local because it involves integration over a compact 2 surface. In Yan literature, these are related to quasi-local energies, quasi-local or.
No, the density is locally defined.
The density is local. Entropy is quote unquote quasi-local because it's over S2 you can think of.
Just understand totally. Is rho supposed to be a d-2 form?
Okay, so I'm writing it in a wrong way. So I'm writing it in one particular way. So if you write completely, so if rho is del L del R ABCD Q epsilon AB epsilon C. So this is a scalar. Okay. So you may think of it as a d-2 form with a bifurcation surface.
Great. So I've got a d-2 form now. Now, can I think of this as a d-1 form defined on the event horizon? We're restricted to this d-.
I know why you are saying this, but I think you can because
certainly Hawking's case you can.
Here also it will can because it will just use the fact that it is d-2 form and certain boundary conditions. I think you can. And you know, there is this what is called the reverse Poincare lemma or something. It says that given any QAB, given any Q which has this made out of local quantities, there is some theorem that it always can be written as. I have to think about it, but probably you can. I'm not sure.
It's not content free in the sense that it's a question of if I know what it is here and I know what it is here, then can I deduce what it is? When I integrate like this, if everything was 2-dimensional, this and this gives me enough data if what I said was right to tell me what happens here. But if you give me a new rule for each surface, then that is much less.
So the curvature is changing at each surface. Yeah, I see. So I have to think about it. I cannot give you the correct answer.
One of the beautiful things about the Hawking form was that it was a d-1 form on the event horizon, completely geometrical. And then, no matter what surface you choose to integrate on, you just pull that thing onto your surface.
But I think the same, why I'm a bit positive here is that, for example, you can write down another current, G, which is dq. Even here also. That is guaranteed. Because what Hawking, one form you are talking about is, or d-1 form, dual to each other, is actually this G. Okay, so that is also possible here. So it comes from here, and this is guaranteed by what is called this inverse Poincare lemma. Any J can be written as 25.
I suppose we'll see it as you.
No, I am not going to declare this. Right. Okay. So let's take an example. Okay. Suppose I take the Gauss-Bonnet Lagrange in D dimension. So I use this formula naively. Okay. So let me write it. What is this epsilon AB? This will be required. Epsilon AB, you can think it of KLB minus KB LA.
Say, I have one more question. Suppose theta and sigma were both 0.
Okay.
At that point, but some higher derivative was not 0.
Higher derivative of thetas and sigmas.
Yeah, something like that.
So I should.
It's not clear to me that your ambiguity can be completely correct.
Absolutely, you're right. So there could be. I will come back to. In fact, if you look at a paper, there's. So there could be higher order ambiguity. So it cannot be arbitrary. For example, you cannot have ambiguity like theta k equal to the power 4. Why you cannot have? Because this result has to be well defined at the bifurcation surface. So only equal number of k's and L must come.
Right.
That is guaranteed. So you can have a quantity like theta k square, theta L. That is guaranteed. It could have. These are linear order ambiguity. There could be higher order ambiguity.
And I suppose I was asking for higher numbers of derivatives.
Okay, you can have ambiguity, but maybe I'll comment on that. So basically, the way we are defining the constraint, we'll stick up to here. What will happen? Okay, let me give you the answer a priori. If you had this higher order term, this will add more than higher order term in your second law. Okay. So then you have actually, so then what you have to do is that at every order you have to fix up your constraint, satisfy your second law, and then wait for the term. So you have to add infinitum of those terms. You cannot stop at second order. That is what will happen.
So, I mean, up to fourth order in the Lagrangian, like for Gauss-Bonnet, if I call that fourth
order.
Sorry, up to four derivatives.
Four derivatives.
Excuse me. So up to four derivatives.
Special derivative.
Then the ambiguity can be entirely.
Any theory, there is a linear order ambiguity. It can always be packaged into this form. Even for Gauss-Bonnet. For example, I can always add a term like this. Always.
Even for
general relativity, I could have
what I
said.
mean is, would it correspond in effect to a higher derivative
No.
term?
For example, in general relativity, I could have added this term. Even in general relativity.
What about something gradient of theta squared?
Yes, you could have. You could have. For
You could
example,
have theta 0 at a point, but gradient theta squared
so
not 0.
di for di for the surface derivative, you can have things like this.
Yeah, exactly.
This kind of terms is also possible.
Yes, why I still haven't understood why these are being ignored.
So these are not ignored. So these are then if you add those terms, what will happen?
So let me ask me, if you add, say, squares or derivatives, the coefficients of dimensions, I imagine, right?
Yes.
Because there will be a mismatch, and they will scale. These terms will scale differently as I scale up the mass of the black hole. So, for a big, because
the thetas will depend on mass.
So for a big black hole, in a big enough black hole, there should be a sense in which additional derivative terms are less important.
So why can't the temperature of the black hole absorb up those dimensions?
Because you can have 1 by m also, right? Or m. You are saying everything should go as m, which is actually true.
Because can be dependent on the temperature.
Yeah.
So why this term? Maybe I will come at the end. Why this terms are there? So suppose you fix it. So you can form this for Lagrangian. You just put it into this formula. So you get this result. So just blindly put it here. Use epsilon to be this. Calculate the functional derivative. It will be like this.
Sorry, I missed. What have you done?
Take the Lagrangian. Use the word formula.
Okay.
Just. You will get this. You will get this.
Yes.
Now there is a geometric identity.
Sorry, and RAB here is
Full curvature.
full spacetime.
Full spacetime curvature. Not intrinsic. Intrinsic curvature will come in the next slide. And you see there are always equal number of K's and L. Otherwise you are in trouble.
That's just supplementary.
It's what happens that if you do a Lorentz transformation in K to lambda, that will happen. Now there is a geometric identity which relates this quantity with the intrinsic curvature of the cross section. And this identity is values. Look at this theta and terms. So what you can do is that instead of this, okay, you can define a new entropy, which is just the extrinsic curvature. You will not see the difference for stationary. That's the point. Okay.
And the identity relating back to that uses stationarity.
No, this is just a geometric identity. Nothing. It doesn't. It just uses null surface property. So note that stationarity will use theta k and sigma k to be 0. Then whether you are using this or you are using this, it doesn't matter. For example, if you have a 5-dimensional...
You're using that the extrinsic curvature is... No, okay, this sounds like Gauss-Kodachi roughly.
This is Gauss-Kodachi for null surface.
Why am I not saying extrinsic?
This is extrinsic curvature. Okay.
Okay.
So this is a null surface. Okay. In null surface, you can have two kinds of extrinsic curvature. So theta, you can think of trace of the extrinsic curvature. So basically, you are having KAB.
Here.
Oh, sorry.
Camera only sees.
Where is your... I always confuse them. So you are absolutely right. So you have these terms like KAB. Okay. With a new index now. Why? Because this is codimension 2 surface. This new index can either take L value or K value. Okay, so you have a term like K AB, K, AB, K. So this is the extrinsic curvature along the K dimension. So it's a codimension 2 surface. The theta is defined as stress of this extrinsic curvature, and sigma is defined. So KAB as sigma AB plus gamma AB theta K T minus 2. So this is the stressless form, stressless symmetric form. That's it's a bit odd compared to the standard notation, but because this is very clear, because when you put it's done because we want to relate it to the Ricciotto equation. That's what this notation has been used. So these are actually extrinsic curvature. So it's a codimension 2 surface extrinsic curvature. Now you see the point. The point I'm trying to make is that if there is a stationarity, the extrinsic curvature goes to 0. Then you could have done it this also. In fact, the first paper, okay, so let me give some credit to my postdoc boss. Some first paper who actually shows that black hole entropy beyond general relativity contains higher curvature correction. This is done for Lovelock, Jacobson and Myers. They actually found this entropy because they were explicitly putting stationarity, so they don't even see those terms. Okay?
Jacobson was
so some credit, because he is very unhappy. Nobody calls it Jacobson entropy. Everybody calls it Myers entropy. Okay, I would be happy if they call it any other entropy. All is black hole entropy. So you can define a Jacobson-Meyer entropy, which is walled entropy plus this ambiguity terms. Here A is +1 and B is -1. Then this would be your black hole entropy. The point is that you can define entropy like this or entropy like this. Stationary black hole, no difference.
I'm a little confused about something. Sorry. Let's go back to the previous transparency. So from that action, you define your S wall, right? That's fine, that's well defined given the action. But S black hole at these two parameters A and B, right? Can you then go to the next transparency?
So next transparency is a geometric identity.
So that's a geometrical identity. And JM is the analog of the walled. I mean, you're going to come to SBH.
Yes. So it turns out that what I'm making is that you can also define another expression using this geometric identity, which will exactly agree with the walled entropy for stationary black hole. So if you do it stationary comparison law, like walled
it doesn't have this extra term.
So because this extra term should be 0.
No. But JM is certainly different from the wall, right?
By this ambiguity, this coefficient. What the point is that these are exactly they are packaged as the ambiguity. So I'm giving you an example where these ambiguities arise and how ambiguities are 0. So both walled and JM entropy obeys the first law of walled. The ambiguities do not matter for stationary comparison law. That's the point. But even for linearized propagation, these ambiguities matter because suppose you take the derivatives, d theta d lambda into theta L, you will see that it will matter. So one of them will obey the second law. And it turns out, let me tell you a priori, that it is the JM entropy which obeys the second law. So the a priori, the naive use of walled formula will not give you the right answer for black hole entropy. If you want second law, of course. This is me and Aaron proven it for. Okay, it is not proven for general higher curvature theory. Now Wallace approved for even general higher curvature theory. We had proven it for sufficient little. All second derivative theory up. Okay, what we call the second order curvature theory. Nomenclature is very different. We call it R square as a second order theory. The fourth derivative theory becomes second order. Thinking of it the order of curvature.
I see. So just to understand, Jacobson-Meyer entropy defined as you have written here.
As I have written here.
So it involves the curvature on that bifurcating. Intrinsic curvature on the bifurcating. Whatever.
Not only bifurcating, but any cross section. It doesn't matter.
Any cross section.
So it is just in any ordinary stationary black hole, it's just 1 by R square. Because the curvature is S2.
By any cross section, you mean you could have added some null direction?
Yes, so you could have extended by killing isometry to any point. Wiggle also.
And the parameter corresponding to alpha will come from the second order term.
What is alpha?
Here, this alpha.
This alpha.
Yeah.
This is correspondent coefficient. So if alpha goes to 0, this goes to 0.
So in general, that will come from your second order terms or whatever order. And your point is that this is what will satisfy the generalized for
the second law.
Second law, at least for
linearized potentials,
regardless of what alpha is.
What alpha is. Okay. So that is equal. So there is no constraint you obtain for alpha on linearized potential. It's not bad.
The Jacobson-Myers entropy that you are talking to, like you take the action, then what are the prescription you follow?
Okay, good question. So honestly speaking, I don't have a prescription.
Just you have to add the ambiguities.
So you have to add the ambiguities, fix the ambiguities by second law. It turns out to be equal to d minus 2 RKS for loss one. Honestly speaking, I don't have. That will be actually really great. For example, it's really great. Is there a total derivative term you can add to the action which will give you this extra term as ambiguities? So then you have an action prescription of getting this entropy. I don't know. This is this kind of thing I am interested in. You see what I'm saying? Is there a definition like this? Where is that? I can give for Jacobson-Myers entropy. Honestly, I don't know. For example, if you have f of r theory, this itself will be enough. You don't need to add any ambiguities. That is simply because f of r you can write it as general relativity plus some skill, non-minimally comes skill. So everything will just factor out here. So that's, I do not know. That will be a very good thing. But it is difficult because there are several ambiguities. Which one you will choose? Everything is packaged into here, but there is ambiguity in deciding the total surface term. There is ambiguity in total derivative term of the Lagrangian. So, yeah. So I don't know how will you balance it. There are several solutions. I don't know the answer. Okay, so now
and this obeys linearized second law only after integrating over the eventualized?
I mean, what do you mean by it? You mean,
Hawking's area increase theorem works locally.
This is local. No, okay, so we call the global, the integrated version, we call the physical process law. I avoid. So this is local. So, this is local.
Are you sure there's no total derivative? In his talk at first.
No, okay, by the way, I should tell you something. What is interesting is that if you're only talking about linearized perturbation, the only JM entropy will obey a total, the local increase. Okay, I'll come to the derivation. But if you look at global increase, still there is no local derivative. The difference will be second order. Let me tell you why. Look at these terms. If you are using short shell coordinates, see, note that I am using only short shell like coordinate. So bifurcation surface is actually not covered here. Okay. You may think these terms are linear order in perturbation. Why? Because theta L is non-zero even for short shell. Theta K is 0 for short shell. So you think that this is linear order in perturbation. Now, write down your Kruskal diagram. This is a bifurcation surface. Okay. So your theta K is 0 here. Theta L is not equal to 0. This is for future horizon. What about past horizon? Theta L is 0. Theta K is not equal to 0. Okay. So what happens at the here? You must have theta K, theta L both equal to 0. Okay. If you write it in Kruskal coordinate, you can see it. So what means that if you actually evaluate this on the cross section of the bifurcation surface, then this term is actually second order in perturbation, not first order. Okay. So therefore, if you do the global change, the difference becomes second order. It drops out.
Difference between what and what?
I mean, if you calculate, so integral, so if you ask this question, that bifurcation surface to some lambda f, okay, of the change of, okay, so TAB, KA, KB, so, okay. So I mean, you're integrating of the entropy change from bifurcation surface to infinity.
But this is what you're doing, but what is the difference? When you said the difference becomes second order.
The difference between, if you do it for Jacobson-Myers,
that's what
minus
wall.
So both of them satisfies integrated version of the second law, total linearized second, which you call Clausius law.
So locally they differ by first order, but by integral differ by second order.
That is happens because of this geometry, because your prescription
endpoints,
your prescription for integration is that you always integrate bifurcation surface. And
just let me ask this again, because that was not my impression, that I probably understood wrong. If you take a little area enclosed by some generators of the event, right?
Okay.
And follow it, have you shown that this entropy increases bit by bit?
Bit by bit, locally, along every generator, rather you can say the statement.
And in this generalized proof by Wall, I explicitly asked
even for generalized proof for world also.
You did ask.
I explicitly asked him this in the string talk, and he said,
What
no.
did he say?
He said no, it's only after integration.
No. It is okay. Yeah, he is right because if it's generalized proof, he actually okay. There is a stop. So in this derivation, in our paper, there is no use of this law. It's a direct hardcore calculation. He actually calculated. But if you look at his paper, the gravitational essay paper, the problem is that you can do it for cos 1, the explicit calculation, when the entropy is d minus 2r. Once the entropy is more complicated, you cannot do it explicitly. But he then uses a result that if there is entropy density which obeys this integrated version, he can reverse integrate and show there is entropy density which will obey local version. So in his gravitational essay paper, he actually assumed that the global version is true. From there, he come back to the local version. In fact, the first page, you will see that he said that I assume that the integrated version of the physical process law is true. From there, I reintegrate back and calculate on this. So I think his paper just remind. I'm sorry that. But this calculation, what I'm going to show you, I'll just show you now. There is no assumption. It's just blind brute force calculation. Okay. Now I'll take a detour. So this is the detour where I'm less confident. Okay. So you know much better than me here. So this is what is called the holographic entanglement entropy conjecture. This is no longer a conjecture anymore. It's just a lemma from the radius CFT because of this Malasen and Lewis paper. So this is a time frozen shot of the radius boundary. This is the art direction. And we all know that there is some entanglement entropy of a region in quantum field theory. It is given by the minimal surface, assuming the minimal surface exists, that radius is time independent case, you can show that it always exists. Then the CFT entropy, entanglement entropy of this quantum field theory is given by the area of this minimal surface divided by the bulk minimal constant. This is absolutely nothing to do with that. Okay. Because this is not a cross section of an event horizon, this is a time lag boundary. Okay. But nonetheless, it's a minimal surface, a co-dimension 2 surface. And there are this appropriate generalization, so many people have written so many people. Except an apparent similarity with Battian entropy, a priori nothing to do with that. Apart from this apparent result, when you ask if there is an event horizon, what is the minimal surface for stationary example, then event horizon and circle diagram. But in a general geometry, well, you can define it even without that. Okay. So the point being is that since it's a co-dimension 2 surface, you can introduce the same here. You can introduce 2 null normal. Okay, but now the surface is time lag, remember. Earlier your surface was null. And you can write down that given a higher curvature theory, what will be my holographic entanglement entropy? Higher DOM. So you use the prescription, the Euclidean action evaluated at the boundary is same as the e to the power z. For the participles, sorry. Okay, and then use this replica technique, use this stack of manifold. Okay, then C1 is the original spacetime, C2, 6, C4 there, and row and then row. At the end of the day, you have this structure. So you give this Lagrangian, which is the second order, most general, in my input lingo, it is second order curvature Lagrangian. Your holographic entanglement entropy can be written as a world part plus distance. Okay. Not that this is a result where P and Q are obtainable from the calculation. What DOM actually calculates what is P and what is Q given your theory. And this world part exactly looks like this, and theta k and theta sigmas are given by this the extrinsic curvature of this co-dimension 2 surface, which is now at the boundary. It has nothing to do with black hole, but you can write it in the same form. This is a form which DOM will write. Here P and Q has not ambiguity, they are just,
Sorry, say that again. So he takes this bulk Lagrangian,
yes.
4 derivative.
Okay, just to make it sure, if you look at his paper, he uses the basis he uses is a time lag and space lag basis. Okay, But if you can convert it to a null basis also, adding and subtracting, then you can rewrite his formula for entropy for a higher curvature theory. This will look like this.
And so what he does is he does the generalization of Ryota-Yanagi, which you get from the replica.
I would rather say the generalization of the Mallasina.
Yeah, which you get from the replica. Okay, Mallasina and or whatever. And then he gets this one.
And there are several issues of this derivation which I have no idea. In fact, I would love to learn from this. There is this regularization of this higher curvature terms around a cone, which somehow magically works. So I probably Holography using all this calculation is wrong, but I don't know what it is or something. Because Holography calculation seems to be saying that if you have a total derivative, you are getting non-zero contribution to the action. So I don't understand that controversy, but take this formula on faith, and I think he's right because of my result. Okay, I'll tell you why. So you get this formula.
Just out of curiosity, and then you must go on. Just to keep everything well defined in the bulk, do they take a kind of distributional geometry?
Yes, tell you there's Grubbs cone geometry, exactly the same.
Maybe it should be possible to make it all rigorous.
Maybe I have not understood that paper. There is this. So in this z minus coordinates they use, there is this component of curvature. There is a conical singularity. Then there is this regularization involving those curvatures. That part is not very clear. It could be my inability to understand, but I haven't.
Almost certainly the case that as you put in higher and higher derivatives, you have to be more and more careful about how you desingularize.
So then there is a comment in Holography literature, this is not unique, you could have done it in different ways. Yeah. Okay, I do not understand that, so I took my hand up.
This bifurcation,
there is no, it is at the boundary. There is no bifurcation, null surface. So this B is just a cross section of the ADS boundary. That's all. So please understand, this has nothing to do with, as I said, evaluating the cross section of the time-like boundary of ADS. This has nothing to do. Now let me go to the crux of. So this P and Q are not ambiguity. They are given by dom. Okay. Given action, you can calculate it. They are proportional function of this alpha, beta, and gamma, proportional to the functions of the dimension. And obviously, if you calculate this for general relativity, P and Q are zero. You can show that in general relativity, this reduces to area form, and this P and Q are zero. Otherwise, there is no harm.
And this action of R square is, there is no ambiguity in alpha beta, or it is only causal.
No. You have to choose a specific values of alpha beta, only then it becomes causal.
And causal is the only constituent, isn't it?
Okay, that I don't know what it is. It's a choice of a classical theory. Causal is the theory which gives you second order equation of motion and second order in time. The initial value formalism is well defined, blah blah blah.
I don't know. In 3+1D, after field redefinitions, can you put all 4 derivative terms?
This arability is not you can.
So in every dimension.
Yeah, I think.
So can you complete this statement?
You can do field redefinitions like G mu can go to G mu plus something times R mu and so on. And so then with that you can mix the 2 derivative and 4 derivative. And I believe the statement is that in any dimension you can write after a field redefinition the general 4 derivative case as corresponding plus Einstein.
It's very easy to see. Because we vary Einstein action, you vary it by the equations of motion. Equation of motion is RAB. Anything that is RAB times something, in fact, can be absorbed into our field redefinition.
In fact, the field redefinition is exactly this.
Yeah.
That GA is equal to GMB class anyway. That is exactly the field redefinition, which will make the thing works. So, now you see that, now I'll give you the result. So this is the result which I am first going to say. In the black hole horizon, I have the same form, where A's and B's are, this is one of the reasons why I stopped here. Why I didn't go to theta k square, because I want to compare it with the so-called holographic formula. In the HE calculation, you have this form of the holographic entanglement, where P and Q are given to you. They are not ambiguity. Let me again retaliate. These theta k's and theta l, these theta k and theta l's are different objects. My proof is, if I impose general second law on this, what I find, P is exactly equal to A, Q is exactly equal to P.
But the generalized second law will involve adding the black hole and entropy
in an ADS asymptotic condition
to the entanglement of the stuff outside the black hole. Is it?
Yes, so I have not even gone there. This is just classical area theorem. I have not even gone there. This is just classical area theorem.
Oh,
I mean, classical.
So let me understand what the requirement, the condition that A equals P arises from just linearized second law. Oh, you said generalized or whatever.
Linearized.
Just linearized second law. Okay, fine. Now I'm with you now. Okay, good.
Okay,
so very different in a sense. I mean,
it is area theorem. You can think of that. So area theorem will enforce A equal to 0, B equal to 0. That's what you can say. If you, for example, if it is A equal to 0, B equal to 0, area theorem, then only area is enough.
No, but I imagine with the Gauss-Bonnet.
No, I'm not doing Gauss-Bonnet. I'm saying that in general relativity, suppose you are doing this same calculation in general.
Right. But with Gauss-Bonnet,
A non-zero, and A and B will also be non-zero. In fact, you know what is A and B. A will be plus 1, B will be minus 1, and you will see exactly the same thing here also. It is exactly matches. That's the case. So before I say that I have proven holography from Laplace thermodynamics, all this bullshit, this is the exact. This is the exact. That the functional form, second law, seems to be exactly imposes the same functional form as I would have got for holographic entropy calculation. The rest is just a derivation of this. Yes.
Anyway, later over lunch, but almost begs for some asking for a generalized second law.
I will come back. I will come back to you.
Good.
So may I have a cup of
Please.
chai?
Go ahead.
No, let's go ahead.
Yeah. You go ahead. I'm just coming in a minute. Sorry. Go ahead.
Okay. Now let's start with the.
You want milk? Huh?
Oh, so that's all.
Okay, with coffee, you
anything which is liquid.
Coffee, make it coffee.
So this is the.
What? You want milk?
That's all. So just whatever you have added.
Okay.
So how many?
That's all. So you have a question.
Yeah. So this ionography can be somehow related to the anomaly coefficient. Why
Yes, it is. It is. Yeah. So I may come back to this later, but yes, it is. Maybe I. Okay. So as I said, this is the result. Look at for GR, the consistency is trivial. So in GR, suppose I have a GR solution, then the bulk is GR solution, boundary is ADS. What is the holographic entanglement entropy? You can show that this is just the area. That means P and Q are all 0. No, the original Ryo-Takanashi prescription. Come back in general relativity, black holes in general relativity. If you want second law to hold true, you have to have area as entropy by Hawking area theorem. So therefore A and B must be 0. So in GR it is trivial to see that they are same. Now let's go back and higher order in GR. So this is my black hole entropy. How do I write it? I write it as an integration over the bifurcation surface. Okay. Often look at the entropy density integrated over the area. Okay. That's the result. That's the expression. So in principle, if you have general relativity, rho is 1. Now I want to calculate the change in entropy. What is change in entropy? I vary the entropy, 1/4 reason antecedent. When I vary the area form, I get the theta. Okay. That's just the, so basically, okay, there is some difference. Okay, I should be a little bit careful. So in the second line, in calculating second line, I should say, so instead of rho, think of it as 1 plus rho. Typo in the, where is the, so there is a typo in the first thing is, yeah, so you may, I think you may ignore this term. There is no theta here, just ignore this. Okay? So there is a typo in the writing. So let me write, so after this flashing this rubber, let me show the mathematics of it. I write down the entropy to be integral over some rho. Rho for general relativity is 1. I have integrated over, so this integration over done at cross section of the event horizon. What is the rate of change of entropy? So this theta k is a typo, you can ignore it. Okay. The rate of change of entropy is integral when I vary dA, I get this theta k, rho remains constant. Where I vary rho, I get d rho dt, where t you can think of a affine or non-affine parameter along the horizon. Put rho equal to 1, you will get, ignore this theta k, you get delta S is rate of change of theta k. It's the rate of change of area. That's a general way of writing it. You define a generalized expression, generalized expansion. What is generalized expansion? Is this. Again, ignore this theta k. There's a type of this theta k is wrong. So this is like this. What is the meaning of generalized expansion? If you put rho equal to 1, this is exactly rate of change of area. Then the Riccioldi equation holds true. Otherwise, it is some rate of change of entropy per unit entropy, which becomes rate of change of area per unit. It's just a definition. Okay. Again, you want that, since you want your future is asymptotically stationary, that means both theta k is 0 and anything derivative with respect to the affine or non-affine time is 0. Because all the derivative must vanish at the future.
Let's say rho was equal to 1. Then what you're defining as theta k is that in the second integral over capital C.
This C is the cross section of the event horizon.
Or is it over the entire duration?
No. This is cross section of. Oh, this integral is over. Sorry, you're absolutely right. This is wrong. This integration is over the cross section of. Maybe I'll draw it right here. Okay. Thanks for pointing it out. There were some typos. That happens when you prepare the question in the last step. Where is that top? Here. So let me do it here. Your entropy is integral rho root sigma d2a. Let's do it in 4 dimensions, it doesn't matter. Okay? So it won't. So general relativity rho is 1. What is delta S? So this integration over a cross section of the event horizon. Delta S will be integral of the event horizon, integral over dt along the path, and then when you vary this guy, you get a theta. Root sigma goes out into rho plus d rho dt root sigma dt dt. That's the rate of change of it. Okay. So if you put rho is 1, this is just give you 1/4 integral theta dt.
And that is that middle term. Theta k is really theta and that.
So I differentiate between theta and theta k because there could be another theta in the L direction. So I explicitly put in the subscript.
This capital theta is time derivative along the
along
the generator.
There is no more killing, it's along the generator.
Yeah.
So basically, in small theta will be change of entropy ddt. Okay. So you make it delta S. That is your capital theta.
Now these generators are very special for Einstein gravity. So in general, you might wonder whether the direction of flow also changes.
Absolutely. So there is an assumption. Not only that, there could be more non-trivial thing, which I should say. This is something which me and Xian Kaman was trying to understand. You see, the event horizon is a null surface. How do you get the null surface? By looking at the matrix. But in matrix, like looking at the ambient matrix, you solve the null surface equation. Now, suppose you have different species like gravitons and photons. In general relativity, there's a strong equivalence principle. Right? Everything obeys, even if you perturb around curved geometry, both graviton and photon will see the same light. That is not necessarily true if you have these higher curvature corrections. So then it is not even clear that which event horizon is a causal boundary, because you can have event horizon for graviton inside event horizon of a photon. This is something which you are going to follow. It's very easy. Take a Weiter solution, write down the event, take a mass function and write down the graph of the event horizon. Write down the graviton, the metric graviton sees, and solve. You will see that two event horizons do not coincide. They are different null surfaces. Both of them are null surface with respect to the metric they see. Okay. Now there is a condition, which one is causal boundary? Of course the answer is quote unquote whichever is inside. So you can have a region where you cannot send gravitational waves, but you can send photons. Okay. So that has been completely ignored. But what you can show is that most probably, I have a very hand-wavy calculation, I cannot prove it. that probably doesn't matter in the linear order calculation. It probably matters in the higher order. So therefore, those constraints which I am going to tell you, they are quote unquote subjected to that assumption that I have chosen. It is possible to choose R event horizon which is inside, and therefore that's the causal model.
There's maybe another attitude to this. If you're working in an alpha prime expansion,
Okay.
maybe I do, but if you're working in an alpha prime expansion, then we know that alpha prime equals 0, the distinguished surface is the unambiguous surface. So then, if your surface moves around, assuming there's some surface, if the surface moves around order by order in alpha prime, you can deal with that by Taylor expansion.
In alpha prime.
In alpha prime, you can choose any surface that's near the event.
But then it's like all this result becomes also an expansion in alpha prime.
Yes. Presumably, in the end, there's nothing more than that.
Probably yes. Okay. Okay. So the mathematics says that final state is stationary, so the lead derivative of dynamical field vanish in the future, so the future value of theta is 0. That's all. So now what I have to prove? I have to prove this one. This is what I have to prove. So I have to, if I can prove this, if I ignore this, so epsilon, you can think of a physical explanation of this explanation. This some bookkeeping parameter which fixes your potential. Suppose you have a mass small m going into a black hole of mass capital M. So there's m by m is your potential parameter. You can think of it. So if you can ignore the second order term, these are theta square, sigma square, and whatever junk, you impose the energy condition. Again, this is negative. Again, theta is 0 in the final. You have theta to be positive. That is what you want to prove. It's as simple as this. So you calculate, given your capital theta to be this, again ignore this theta k, you calculate this d theta dt, you get this mess. You get some terms which may have actually first order condition. I mean, may not be proportional, they may not have any fixed sign. Okay. So ideally what you want is that, so you write down this term, this looks like this, where hkk is the part of the field equation where you subtracted out the Einstein's equation. Einstein tensor. So this is basically the higher curvature part of the field equation. Not that if rho is...
Without matter. What do you mean? No.
What do you mean by that?
HKK is with
No.
TU and contribution.
So what you do is this.
Is that right?
So what you do is this, you write down your field equation to be GAD plus alpha HAD equal to TA.
Oh, okay.
So that HAD comes out here and then the HAD part is there. So ideally, if you have general relativity, so if the linearized first law hold, all the linear order term in this mess must cancel each other identically.
No, I understand why you have the HKK term, but why do you have the RKK
That
term?
comes because there is this theta here, where you take a derivative of that, you generate by a Raychaudhuri equation, you get RKK term.
So even in the Einstein-Hilbert case, you will get that term, isn't it?
So let me check. So I think there is, okay, look at this expression. There is one typo here. It's not consistent. Notation is not consistent. In this case, rho equal to 0 is the GR limit. Okay, because I have separated out theta k separately. So
Okay.
take rho equal to 0, this part goes to 0. There is no EKK at all. Okay. And then you just have d theta
okay.
dt.
I was setting rho equal to 1.
So that is why there is,
Fine.
so I have mixed up
Okay.
LaTeX file from two different layers. Okay. So the correct choice of entropy is that all linear order part in this extra term should cancel. Okay. If it cancels each other, you have this expression and you have linearized second law. That's a constraint. So you write your rho to be world entropy plus A into B. First of all, it is one equation. How you are getting two? How can you compute two coefficients out of one equation? There's one condition. That's trivial actually, you can understand. Since it's a linearized second law, expansion and shear don't mix. So basically they are reducible representations. So you actually, from equating this to 0, you have two separate linearly independent equations. And those equations helps you to determine A and B. So you take your entropy candidate to be this, world entropy A and B, impose the condition that all linear order term in EAB is 0. Do it. And you can and get the A and B out of that. I can do it without even assuming any symmetry. or anything for Lovelock ones. And f of Lovelock, that is my paper in World, that for any entropy density in Lovelock theories, for any Lovelock theory in any dimension, this calculation can be done exactly without assuming any symmetry, the full glory of general relativity. But for general higher curvature theories, I don't know how to do. It's actually simple, you can understand. For all Lovelock terms, the entropy densities are proportional to the extrinsic scalar. So if you change it, you know how to calculate the variation of the extrinsic scalar. They are just Einstein variation.
Extrinsic?
Yes, sir, intrinsic scalar. So think of it that the entropy density is d minus 2r. Change of d minus 2r is nothing but Einstein tensor. You know already, because d minus 2r, you can think of that change of the d minus 2r is due to the change of the induced matrix. So you ask how the d minus 2r changes because of the change of the induced matrix. That answer is just Einstein variation. D minus 2 RAB delta gamma AB plus a surface term. So you can explicitly calculate everything. So that calculation is possible for Gauss-Bonnet. But if you do not have induced intrinsic scalar, like in general higher curvature theory, I need to use a D2.
And what do you do with the surface term?
Okay, so it turns out in linearized order the surface term doesn't matter. As long as the compact boundary is compact.
No, but then you're saying that you're throwing it away by integrating by parts.
Integrating on the compact surface.
No, but then that sounds like it's not local.
Okay. I see. I agree with you. Then it is that integration has been done.
Yes.
On the total. Yes, that part is without that.
The integration has to be done
on theta phi direction.
On theta phi, not time.
Not time, on theta. That has to be, yes, absolutely. Now I see your part. That part I forgot. That part is there. Okay, that's good. So what we did is that we first choose a very simple solution. So we assume that there is a generalized solution exists for this theorem. So what I need a time-dependent solution. Okay. To calculate this quantity, because for ordinary time-independent solution, everything is zero. The only time-dependent solution which contains black hole is Wigner black hole. We know in general relativity. So we assume that some such solution exists. I don't need the explicit form of this f of r. And this Wigner black hole, there is an event horizon, there is this null generator of the horizon, everything you can define. Note that the event horizon is not at f equal to 0, because f equal to 0 is then the apparent horizon. The event horizon is some first order differential equation. So you have to give appropriate boundary condition to determine where is the event horizon. And then you can calculate this theta case and theta l. Look at this theta case. This is non-zero. On event horizon, f of r is not zero. If it is a short-chain black hole, f will be zero. So you can show actually that if you look at entropy change, entropy may be ill-defined with a cutoff dependence, but entropy change, the cutoff dependence goes away. Then you can extend it to a generalized second law. But you need a prescription to calculate entanglement entropy. Modulo that prescription, you can generalize it to. There are certain state assumptions you can have to make on this theory of locality that generators don't talk to each other. So then it is possible, just like, so there is this proof with Wall PhD thesis that, so basically the earlier proofs of generalized second law, the quantum state, was a little bit of non-rigorous. So what Wall did is that at least for free field theory, he can give a set of assumptions. On the basis of that, he will rigorously prove that the entanglement entropy plus area will increase. The difference is positive, and that comes from the what is called the monotonicity property of this relative entropies. Given rho and sigma, you can define two density matrix. You can define a relative entropy, and given an algebra, the sub-algebra, the relative entropy always decreases. So he come up with this idea that you can have Rindler slices and define an algebra. Going into another slice is like going into a sub-algebra. So minus of the relative entropy is then the black hole and the entanglement entropy. It's a prescription, of course, and it only works for free field. Okay. There are some other examples he has given which I do not understand. Some other crazy field theory in 1 plus 1 dimension where these assumptions are true. But if you model to certain assumption, you can jump into semi-class.
So this was this was with the higher this R square with gravity with R square term, free theory, free scalar or something.
What do you mean by free scalar? I mean, this is for this. Okay, I don't know this nomenclature. This is for this theory.
No, but why you said free theory?
Okay. Oh, sorry. That is in the semi-classical context. So, semi-classical context, you have to define not only this classical entropy, you have to add the entropy of the matter fields, which are propagating in this black hole spacetime.
Those are free.
So, as long as they are not interacting with each other, okay. And also, you have to you cannot include gravitons. Okay.
I was going to ask.
You cannot include gravitons because gravitons. What I do is that you can bypass
free fields as linearized.
But they only contribute to the shear, and shear is second order in some sense. Okay, so there is a derivative expansion even. There is an expansion even there also. That's the way it comes to. So there it is very restrictive. Okay. But nevertheless, actually there is no other proof of such law. If you really want to be bigger. Okay. So therefore, if I give this entropy, so this is what I have written. It's a little differently.
Just to say about that, sorry, I'm late, but some of the work that's going on is towards understanding entanglement better for weight systems, including gravity, and then maybe it feeds into this, because you don't have to work in those centers and so on. Anyway, good.
But whether this assumption for free field will translate into something that I have no idea. So here is the result. So even if you include, forget about this holographic entanglement, there is a classic GI result I can define for you. If I have this theory, alpha, beta, look, I have written it a little differently. I have written gamma into Gauss-Bonnet. There is a repackaging the coefficient. Then my correct black hole entropy for non-stationary slice is this. And
let me just try to listen. So you start with that
Lagrangian.
And you fix the ambiguities that
ambiguities.
Choose the coefficient of the generalized.
And then it looks like
linearizable as this. And then it looks like this. Where
okay, now you put general relativity. You put stationarity. That theta is 0. Theta k is 0. It is only this part. Okay. So you see that if beta and gamma are 0, if you have a pure R square theory, there is no ambiguity. All A and B will be 0. So, because R square theory is nothing but general relativity in disguise. Doesn't matter. So, and also you note if you put alpha and beta equal to 0, then you have pure Gauss-Bonnet theory. You just have this t minus 2r. So that's why I have written it in this way. So the claim is that this is the black hole entropy for non-stationary slice, which obeys linearized cycle. And of course, and then why you are not adding higher theta k square, theta n square term? Because you say that okay, those terms, there is no such analog of those terms in holographic and thermodynamic entropy. So let me stop here from analogy with that.
That is one, but in the spirit of your own discussion, maybe you would like to argue that had you included them, you would violate the.
No, you will not violate the linearized second law.
You would not.
No, it will
because
not.
why is it?
Because they are higher order.
Oh, so they don't. So you can't test that. So
you can't test
the better way to say that is.
You can't test that by linearized second law.
Yeah.
But when I go to the next order, if I added those terms, so my up to this they are independent of those terms. But my next slides are subject to the assumptions that those terms are not there in that entropy. That assumption I can only justify by saying that if there is some holographic, if this is the theories at boundary and bulk know about each other, then I better stop here.
Sudipta, just one. If we want lunch, we're going to have to stop.
Okay, so I just maybe
Actually 1:30 I request because
I can go on.
Just the previous.
Yes, sir.
In 4 dimension, Gauss-Bonnet contributes to the entropy?
No. That is a good question. Okay. This is like provocative question. If you write down this formula, of course it does. It gives the Euler number of the horizon. It's a constant, right? 2 or S2, right? So it does not contribute to the change of the entropy, right? In my calculation, it will not contribute, just adding an additive constant. But think of the calculation where 2 S2s, 2 black holes coming from infinite distance and merging. They will contribute. 2 plus 2 will become 4. So there is a discontinuous change and area increase, so you can arrange situation where you can actually decrease the black hole entropy. Okay. There also gives another bound on alpha. You should see another of my thing. Okay, that's what it is. So it indeed does up to a constant multiple. So on this way of looking at linearized second law will not contribute to the entropy change. But you can think of scenarios, a topology change of the horizon. Okay, this topology change is not quantum gravitational topology, just marching in that. Okay, so as this is the point, so this entropy differs from the naive Boyd formula and obeys linearized second law, and functionally exactly matches with the holographic angular entropy. If you ask me why, I don't know, but it's very interesting. Why would it match? There's absolutely no reason for this to match. There must be something very interesting thing going on. Okay.
So now you've used linearized analysis, but you've completely fixed the coefficient. So this, if there is a formula for the nonlinear theory, this is it.
That is it. Now I want to look at the second order perturbation with this fixed entropy. That's the game. You fix the entropy. Now look at, from the linearized second law, look at whether it satisfies the increased formula in the second order, next order in perturbation. That's the game. So if you do that, you see that for general relativity, for example, the second order terms looks like this. They all have definite sign. And note that you have to have them negative sign, because you can think of a shell which has entered into the black. Okay, so after that shell has completely entered, TAB is 0. So it's not that they may have positive sign and then total term is negative. They have to have strictly negative sign. Because then after the shell entered into the black hole, you will have decreasing. The d theta d lambda negative condition is no longer valid.
The shell could be gravitons.
Okay, it's not. It's not. That's another way of looking at it. There's no matter case. Everything is in the shear. So there is this nomenclature which general relativists use. They call it this as the canonical crystal. Okay. Including the gravity. Okay. So if you do it for our entropy density, the same good old sigma, you get this. But this zeta is some function of this curvature and everything, okay, packaged together. Okay. And then you separate out the, so this has a non-zero. The important thing is that it does not have any thetas and sigmas. As if otherwise I cannot make this statement. This has a linear order term. Zeroth order contribution in the background. Because you are thinking of everything perturbing around the background. The background is stationary. So what you want now, your constraint is the zeta evaluated over the background must be positive. So earlier constraint was EAB, linear order term goes to 0. Now the constraint is you want this. And let's see what it gives. So you take different values. The simplest background for Gauss-Bonnet theory is the so-called Bulwer-Liptazov solution, which is a generalization of the Schwarzschild black hole. Okay, this is just if you take alpha goes to 0, meaning it goes to Schwarzschild black hole. The event horizon is at there, 5 dimension. Don't worry about the crazy unit because it's 5 dimension. Okay? What does the negative sign? Okay, so event horizon, the black hole only exists only when m square greater than 4. You impose this, you get m square greater than 4. That is very satisfying. So if you are actually perturbing over a true horizon in asymptotically flat space, you have at least for this very special restricted class of particle. You can remember that I have assumed a symmetry. I am perturbing over a spherically symmetric graph. Okay? That's important to understand. And this not only that, here I am ignoring the sigma square term. So the perturbations are assumed to be spherically symmetric, just to control the calculation. Okay? So there could be. So this is a necessary condition. Need not be sufficient. Okay? So you get m greater than 2. The second law up to second order holds when you perturb around a true horizon. That's very satisfying. This like has to happen. But the interesting thing comes when you have ADS black holes. So this is this ADS black hole with different values of k. R0 is where the black hole is. K equal to 0 is the planar black hole. K equal to plus minus are given hyperbolic, spherical black hole. These solutions can be embedded in your string theory. And then if you impose this, you get a condition that lambda GBs, which is some normalized. So given the prime, you normalize it with respect to L square because you want to make connection with the known literature, and then you get this form. GB must be less than 1/10. So this bound has to be obeyed so that second law around these black holes holds true. That itself is very interesting that this is the first time from second, at least for black hole thermodynamics, you are getting a bound. But do this bound arise anywhere else? And the answer is yes. For example, there is this papers which looks at instabilities in the holographic fluid, exactly which are dual to this theories. And look at the signs of the Schrodinger potentials. Okay, basically looking at whether it can support the unstable quasi-normal modes or not. Exactly, you find the same one. So it's a bit uncanny. Why would that happen? Look, the holographic entanglement calculation means now if you look at perturbations of the holographic fluid, you get this consistency condition. There is a graph emerges. If you look at, for example, the k equal to minus case, you get this bound in 5 dimensions. This is exactly what the bound you obtain, the causality violation in boundary theory. The speed of light in boundary theory, it's a relativistic field theory. The speed of perturbation in boundary theory should be bounded by 1.
I was actually going to ask that for the planar case, the bound you get from your considerations or from the sound
challenge.
How do they compare with the causality violation?
So causality bounded, I think they don't match with the causality. I do not understand.
Which one is more constraining? Your constraint?
This is the biggest constraint. Yeah,
well, this seems to be for a hyperbole.
This is the strongest bound.
But even in the planar case, causality violation should give some constraint.
I do not know that constraint, so I have to look at it. I don't know.
So for the sphere,
there should be
causality violation.
But I have to look at it whether they what is.
Which was the constraint for positive viscosity? There was one.
That is different constraint. That is lambda greater than, eta by s to be positive. That is lambda less than 1. Because in Gauss one it is 1 minus 4 lambda.
Viscosity constraint was weaker.
Weaker. So viscosity constraint does not ensure.
It's just too low.
So that is my claim. So so if you have this sigma square term, my hope, okay, so we should think that you'll get back the viscosity constraint. So that is a hope. So you don't see that viscosity constraint. There's no.
But you see something more constraint.
So what I'm saying is that theta square gives you more strongest bound. I agree to that. But what I say is that you may, for example, you may think of gravitons where there is no theta.
Just ask where the coefficient of sigma square is.
Where the coefficient of sigma square will be. Suppose you have graviton, there is no theta. Okay. At least so theta square will be part of it.
But nevertheless, your bound will
my bound is constrained. Okay, this is the strongest bound so far. This is obvious we are waiting for explanation. The holographic theory is in the lab. So here is the summary so far.
So far, make it summary. Sorry.
Okay, A. No. So the naive application of Wald formula does not give correct expression of entropy beyond general relativity, except for simple f of r gravity. Validity of linearized second law requires correction to the Wald's expression in the dimensional regime. For general quadratic curvature theory, this correction matches exactly with the holographic entanglement theory. Again, that we get functionally matches. A priori, they are on different surfaces. This has to be emphasis. Okay. Somehow, so when we wrote down, of course, the paper, we gave a catchy title. Holographic entanglement entropy increases. But this is what we mean actually. Somehow the holographic principle already contains the validity of basic laws of thermodynamics, and if you believe in ADS CFT, it's not very unobvious. It has to happen. Somewhere there has to be a relationship between the consistency condition in bulk with the consistency condition in boundary. That's a dictionary. And then there is this point that black holes in ADS space, this second order constraint coming from the consistency of the boundary condition also matches. But I don't know this causality conditions on planar, I don't remember. I have to look at it. Whenever I know, it's very interesting, it matches. This is a way to understand it. Of course, you have to do it for generic perturbation. Calculation on the way. Hopefully, you'll be able to make some statement about what happens with
generic nonlinear perturbation.
Nonlinear perturbation. Yeah, that's what I mean. The second order term, at least, may not be for the non-perturbative way, but it will be great if somebody has a non-perturbative treatment. There is one possibility, as Siraj used to say, that possibility you do it non-perturbative with this expression, but keep it perturbative with alpha prime. There may be, so you linearize everything in alpha prime. So what you do is that whenever there is alpha prime, you impose general relativity.
Yeah, you don't require that we satisfy. You only require that we satisfy up to terms that we correct.
But then I will be not able to give this talk to general relativity audience.
Okay, well, you should. I'm still not sure. Okay, I don't understand how. If
okay, I'll tell you something. Suppose
if the leading change was not already linear in your small amplitude, that is, if you're
so in operational limit,
we have to go for a very hard
there is one point.
Well, I should go actually.
There is this point I should make that there is a very beautiful map relationship with everything. That you know that area I can map it into a statement of the positive entropy production. So the claim is that you use our entropy, it will be possible to generalize this map, or at least for cosmonic chemistry. So I think we'll be able to do it.
Except that your map, you don't have a local increase.
That is true. I have to go
In fluid dynamics, very important that divergence of entropy current is low, positive, local.
Agree. So, but if you, I agree to that point, absolutely no point. Then the question is that there is this Kamano paper which is very disturbing. So they have found that any alpha prime correction is bad.
No, it's not bad.
It's consistent.
It's only bad if you don't have further.
Okay. I mean, any truncation is bad. That's what I
And that's entirely what I'm saying. The constraints you get, which are robust compared to additional higher order terms, are interesting. But allow me to say, if they are, those constraints are softened to order 1, by then
absolutely. So I cannot deny. But this is so what they have found. If you remove that 3-point function, the classical result is that there is a closed time-like curve. And so this is I'm arguing. This is the system they construct. Is it stable under perturbation? Can I destroy the closed time-like curve in perturbation? So, or does it disobey any? Well, you have closed time-like curve in general relativity. We never worried about it because there are violation of energy condition. Is that such happen in their system of this two crossing graviton?
You're asking whether the argument was correct.
Yes.
I agree.
Okay, so this is something. So I'll end with this statement by Ellington, which I find is that if a theory is against second law of thermodynamics, I can give you no hope. There is nothing but this. Only